Welcome to coronavirus video number 2. So there was a little bit of confusion over this slide and what we were trying to get across here. But basically what the question is asking is what happens to FG the closer you get to the center of a planet. And so the analogy I made was let's pretend as if all of the mass above us is gone, and because we know that that's actually an effect, right? Because if you're in a shell, there's no FG from that shell above you, and so it's effectively as if you're sitting on a smaller planet. And the question is, what happens to the FG as this radius gets smaller and smaller and smaller, and the planet gets smaller and smaller and smaller? And the reason why it's not so obvious is that even though you're getting closer, so you're getting closer to the center of mass, which would make your FG go up, because this would get smaller, right? As this gets smaller, the whole term would get bigger. But you also have less mass that's underneath you because your planet is smaller. And so it's not just straight up obvious, and so you got to do a little bit of math. And so what we end up doing is we end up plugging in the mass of that planet based on the density times the volume. And so there's your density, and that's your volume right there. That's the volume of a sphere. And so if we plug all that in, and we do a little bit of algebra, and we cancel some radiuses, right? We basically get this expression right here. And so what this tells us is, as we approach the center, we know that as r gets smaller, my net force of gravity on me is also going to go down, and it goes down in a linear fashion. This also kind of makes intuitive sense because if you were, and actually this is one of the questions, so if you were at the center of mass of the very center of a planet, well, what's your FG? Your FG is 0. And so you know that FG has to go down as you approach the center of the planet. So the next thing that was confusing because I actually made an error. Yes, believe it. And it was with this total energy slide. So if you recall, I explained basically the formula for total energy is the combination of both your kinetic energy and your potential due to gravity. And if you were paying close attention, you would have noticed that I dropped this R just randomly, okay, out of the equation. And because I just copied and pasted this equation, as the slide goes on, the error kind of propagated itself. But as you can see here, I have put the R back in, and now all of that math should make perfect sense. And so you've got the kinetic piece right here, plus your U, and they will combine because they're the exact same terms, right? One's 1/2 and one's -1, and they combine to -1/2. So just wanted to clear that up. Thank you guys for catching it. Okay, so the next thing that people were a little bit confused about, and it's perfectly normal to get turned around when we're learning new words, new vocabulary, etc., right? And this particular topic has a lot of vocabulary to it, and so sometimes teachers forget that you kind of have to learn those things before you can kind of get the material. And so what I wanted to do was to review some of the terms that I used in the presentation, and to kind of explain the differences. All right, and the main confusion is around all these different velocities, okay, and in orbits, etc., etc. Okay, and so for the record, your orbital velocity is when a satellite is in rotational equilibrium. Okay, not complete equilibrium like we've learned before, but rotationally. And so it is traveling around the Earth, right, with a constant speed with uniform circular motion. Okay, it is at rotational equilibrium, meaning that it's not going to change altitude, meaning the distance away from the surface, and it's not going to change its speed. but of course its velocity is changing as it goes in a circle. Okay, so that is orbital velocity. Satellites, when we put satellites into orbit, we launch them so that they will reach the required orbital velocity. Okay. What about escape velocity? So escape velocity is similar, okay, but it's kind of the special case. It's this special infinitely away case, and so to calculate your escape velocity, you basically have to assume, right, that the satellite is going to have an orbit that is infinitely away, and so it basically escapes. Okay, and anything more than that, right, is just going to keep going. Okay, and so by definition, your escape velocity is that initial velocity required to launch it, right, into space. Okay, so that it escapes the gravitational pull of whatever planet or star it's coming from. Okay, so that is the special case escape velocity. Then there was a little bit of confusion over changing orbits. So here's the deal with this. Okay, the deal is that we simplify orbital mechanics. We extremely simplify it for the purpose of AP Physics and for the exam as well. Okay, we assume that orbits are circular, et cetera, and we kind of assume that it kind of magically reaches these circular orbits, right? In reality, this is not the case. In reality, you get these really weird parabolic paths and whatnot, but you got to start small, and so that's why in AP Physics we assume that our orbits are circular to make them math 4,000 times easier. Okay, and so if we're talking about changing orbits, just keep in mind, right, that the path it takes to get to the new orbit is probably going to be one of these crazy parabolic paths. But if you recall, delta E doesn't care about how you got there, right? Whether it's up and down hills all over the place. All it cares about is where you started from and where you end up at. And so that's the bottom line. When we're talking about changing orbits, is we're just talking about our delta E, right, is going to rebalance. So our K's and our U's are going to rebalance so that we are again in, and here's this term, rotational equilibrium, right? And so altitude and speed is not changing. Okay, so by definition, a little definition here, right? So if work is put into a satellite, right, or a satellite is currently not in this rotational equilibrium, if it's not at its orbital velocity, because that's rotational equilibrium, then it will change altitude and velocity until it reaches that balance of rotational equilibrium. Okay? I hope that clears it up a bit. Okay, this last rebuttal video, I guess we could call it. The last little thing I want to talk about, and this is actually kind of cool because of the way that we set it up, right? We solicited questions, and I got a lot of really cool questions. And so what I just decided to do is let's just do a slide where I kind of list your questions, rephrased, of course, and I give you an answer because there were some pretty interesting questions. All right, so question number 1. Would being above the ocean or above a pocket of helium cause your weight to change? What do you think about that? I think that is a resounding yes, because the density and the amount of mass that is below you will be different, right? So the density of water is actually a lot less than the density of rock. Therefore, rocks typically sink, right? The same thing is true of helium, right? So if you had like a little pocket of helium, right, the mass underneath you would be less. Therefore, the force due to gravity would also be less. Note that your mass never changes. Your mass, it's just your weight that changes. All right, next question. Why do satellites fall from orbit? Well, we talked about it a little bit in that this stuff is pretty complicated. The actual study of orbital mechanics is the geometry and stuff going on is pretty crazy. But satellites typically fall out of order out of orbit because they're never really perfectly in orbit, and usually satellites have little thrusters that help adjust, right? And so if it's detecting that its altitude is falling and it's speeding up, right, then it'll kind of thrust to correct their orbit and get it back into the proper orientation. And of course, erosion occurs in space from hitting things, atomic level type things, and there are also collisions that occur. And like I said before, the orbits of these satellites are not really circles. They're technically ellipses, but like I said before, we simplify that to make the math 40 times easier. All right, next question. Can an object in space sit on a planet's orbit and not be moving? That is categorically not true, okay? Because if you had an object that was just sitting there in space, not moving at all, what's it going to do? It's going to get pulled towards the Earth, and as it gets pulled towards the Earth, it's going to speed up faster and faster and faster. And actually, that's going to be one of the problems you're going to have to solve for is, all right, well, what's it going to be when it hits the surface of the Earth? Okay. Last question, and we kind of answered this already in one of the previous slides, but if someone were to be at the center of the Earth, if that were possible, right? Of course, it's not possible because you would basically vaporize at the center of the Earth. But if we could, would they be floating around, as in weightless, since the force of gravity is zero? And the answer to that is absolutely. This is exactly how the physics work. And it's because all of the material above you would be the Earth, all of the Earth, right? And it would all be a shell that's above you. And so, boom, all your gravitational forces are going to all cancel out. So there you go, Super Mario Galaxy. Thanks for listening and watching.